Hello, my name is Thomas Trausch. Today we are dealing with the proposition 3 of the work of Gottfried Wilhelm Leibniz on the quadrature of the circle, the parabola and the hyperbola. In proposition 3, which is another preparatory proposition for a later proposition, namely proposition 7 and proposition 8, where Leibniz is applying the outcome of this proposition 3 for an indirect proof that two different areas within the quadrature of the circle are actually equal. But for doing this, he needs to actually prove the following in the proposition 3. And let's start right away. So we create a series, which is in this case a natural series, because we only have an ascension. When you go from element to element, you will always have a quantity larger than the previous one. So this is natural. And Leibniz says that the difference between the outer quantities, namely A and E, can never be larger than the sum of those quantities of the differences from in between each successive element. And that's what we are going to show in the following. So we create the difference series for this series. So the difference between each of these elements are called F, G, H, and L. So F, for instance, is the difference between the element A and the element B. And it needs to be noted here that we always talk, when we talk about differences, we talk about quantitative differences. So there's no differentiation in terms of a sign. So there's no consideration of a plus or minus. So excess or deficit kind of things are neglected in this viewpoint, because we're only dealing with absolute quantitative differences, so-called. And the theorem says that M, being the difference between the two outer quantities, in this case namely A and E, can never be larger than the sum of all differences F, G, H, L. And that's what the theorem says, and we're gonna try to explain this. So when you would like to express each quantity of each element differently, namely by using these difference terms, then you could, for instance, say that element A is of course element A, but the element B is the sum of the first element A plus the difference between those two elements, namely F. And in this kind of fashion you proceed with all the remaining elements such that C, for instance, of course, is then the sum of quantity A plus the difference between quantity AB plus the difference between BC, and you would end up at C in this case, and so forth. So he's doing that for all the elements and all the differences between the elements. And when you write down these equations like this, you notice that in the case as we have here with a series of natural order, the difference between the outer quantities, namely A and E, is basically this one. Is equal to the sum of all differences in this series. So this relationship is telling us that the difference of the outer quantities A and E in this case can never be larger than the sum of all differences in the series. So E minus A is always equal to F plus G plus H plus L, and never larger than that. And in the case of the disturbed series, we arrange the series now to be a disturbed series because you have a section of the series which is descending and then it's going up again, ascending in the same range of the whole series. That means the series is of a disturbed order. And in the case of the disturbed order, the sum of all differences, f, g, h, and l, becomes greater than the difference m between the outer quantities. And we pointed this out in this example here. Here you see the sum of all differences, in this particular case being 7. And the difference between the outer quantities a and e, which we call m, is in this case 1, because a has a quantity of 4 and e has a quantity of 5. So the difference between the two is 1. And you see already that the sum of differences f, g, h, l is larger than the difference of the outer quantities. And yeah, that's basically what he needed to show. And you basically can test this with any arrangement, be it a natural order series or disturbed order series. You will never manage to make the difference between the outer quantities, like in this case e and a, larger than the sum of all differences. And what's also interesting to note is that the difference of the minimum element of the series and the maximum element of the series, which we in this case called n, and which in our case here is the elements c and e, whereas c is the minimum element and e the maximum element with the largest quantity. This minimum maximum difference, that's basically the largest which the outer quantities could become. Yeah, and the differences f, g, h, l becomes also greater than the difference n, so being the mean max difference between the greatest and smallest term of the disturbed series. And this is telling us that in no circumstances the difference of the outer quantities will ever be larger than the sum of all differences, no matter if you have a series of natural order or a series of disturbed order. And that's what he needed to show. And this particular case is becoming really important in proposition 7 and proposition 8, where he uses this relationship within a series to really do an indirect proof of comparing different areas within the quadrature process of the circle, which serves the purpose of showing that these areas are equal. And we're gonna get to that in proposition 7 especially. So, but before that we have to go through another set of propositions dealing with the series. But so far we have achieved what we needed to show in the proposition 7, really that is the case that the difference between the outer quantities a and e will never ever be larger than the sum of all differences in the series. That's the important message to take away from here. Yeah, and that's basically what we needed to show. I hope you enjoyed it a little, and maybe you watch this twice or 3 times again and let the information sack a little, and then you will certainly notice that there's a content of truth in this proof. And again, we're gonna need this later on in proposition 7. Alright, thank you very much so far, and I hope you stay tuned for the next proposition coming up. Thank you very much.